can press the garbage.
Oh,
This is so silly.
You can move that like zoom like small rectangle so the operators.
Yeah.
okay.
Wait, okay. Okay. We did it.
So joining us today from my mentee is Surya. She'll be talking about Makarama optimal Oblivious RAM with integrity.
Hi everyone, I'm Surya. This is based on joint work with Nikon Lafla. So yeah, Nikon and I worked on the slides together, so huge credits to him. And yeah, today I'm going to talk about optimal Oblivious RAM with integrity, and we call it Makarama. Feel free to interrupt with me whenever with questions. I love questions, and if anything is unclear, just interrupt me immediately.
Why did you choose this title?
Because we use all Macs. Yeah, and it sounded like macaroni. And Macarena. we had a whole like meeting to figure out this title. It's a thing. Anyway, okay. So suppose you have a client who wants to perform some RAM computation, but doesn't have enough local space to do it. So one thing he can do is use a remote RAM server. So there's a server, and he can send read and write queries to this. So when I say a RAM server, I really mean a server that supports read and write queries. So how can we ensure that this computation remains private against a curious server? So what do I mean? So the immediate idea you might have is to encrypt the data. So that means the client can locally store a key and encrypt all the data that's sent to the server. So whenever you get back the data, you just simply decrypt it on your end. But it turns out encryption alone is insufficient for privacy because even your access pattern to the server can leak information. So for example, consider a scientist conducting a medical study. Then suppose his data is organized as brain data, kidney data, and so on. Where you access your data is still going to leak information. So for example, if you see that the scientist is accessing this heart data portion a lot, even if you don't know who the patients are because it's encrypted, you still know that there are many patients with heart issues. So you want to hide even this type of information. Okay. So to combat this, Goldreich and Ostrovsky proposed a primitive Oblivious RAM. So basically, there's a user and a server. There's going to be this ORAM client in the middle. This ORAM client is going to take a read or write query from the user, and it's going to transform this into query hats. So there's a bunch of query hats to the server, and then the server is going to respond as if it was still a RAM server. So you should really think of the server throughout this whole talk as a passive storage. It's only going to respond to read and write query by looking at the database. And it absolutely does no additional work. That's the model we are working with. So now after these read and write queries, the ORAM client is going to determine some response. So for correctness, we want this response to correspond to the read write logical query. So throughout this talk, a few things. Everything with a hat is between the client and the server, and everything without a hat is between the user and the client. I also call these guys logical queries. So all the queries are logical queries, and all the query hat are physical queries because those are the physical accesses you're making to the server. So please, if it becomes unclear at any point, please stop me. Okay. And for obliviousness, you want these transform query hats to leak absolutely nothing about the original query. So basically, another way to say this is that the list of query hats can be simulated given only the number of queries. The only thing that's going to be leaked in this process is the number of queries. Okay, does that make sense? Any questions? Okay. So one possible application is suppose you're going to use some server like Dropbox or Google Drive to store your data. One thing you could do is run an ORAM client locally on your laptop. And now all these accesses here are oblivious. So now the storage platform can't learn anything about your access patterns and your data. Another example is using secure hardware enclaves, which have tiny space. So there's an untrusted server with Encla chip inside, which is small. So this is untrusted memory, but this out here is untrusted. So what you can do is you can run an ORAM client inside the Intel SGX chip so that all these accesses to the untrusted server are still oblivious and still secure. So recently, Signal has actually implemented ORAM for the purpose of content discovery protocol. So this is really something that people have considered using in practice. So in terms of efficiency, there are two main metrics that people care about. The first is local space. So this is the amount of space the ORAM client is locally storing. So this is treated as private and trusted. And as a sanity check, if you have a RAM with n queries, the space n is trivial because now the ORAM can just locally store the data and not even bother communicating with the server. So for the purpose of this talk, think really O1 words, where each word is size log n bits. So really you'll need locally storing log n bits. So if you look in this picture, the local space is what is contained in this middle part here, this ORAM part. The second metric that we care about is overhead. So this is the number of transformed queries, query hat, per logical query from the user. We can think about both amortized and worst case, construction ends up being worst case, but yeah, that's not too important for this talk. But yeah, so that part there is overhead. So again, as a sanity check, if you allow overhead n, it can easily achieve an oblivious RAM because you can just iterate over the full server every single time. So one can ask how well can you like reduce this overhead here? So there's a bunch of works considering this problem. So Goldreich, when he first proposed this primitive, came up with a construction which was square root n log n. Then Goldreich and Ostrovsky kind of take this idea further and reduce it to a polylogarithmic number, so it's log cubed of n. And then there's PathORAM, which is a slightly different style of construction, which is tree-based, which achieves log squared n overhead for word size log n. And the beautiful work of Panorama achieves like very, very close to log n, so close. And finally, Optorama achieves log n. Very exciting, but can you do it any better? And turns out no. So there's a lower bound by a different, like many sets of people with different parameters, which basically shows that this omega log n overhead is the best you can achieve even with computational assumptions. Okay. So yay. Yeah.
Is the ORAM
Optorama. Yeah.
practical right now?
No.
So okay, so which one are the most practical?
ORAM is the only one that's practical. I guess the squared n log n one isn't too bad. It just does sorting, which is log squared n. So like it does a nicer sort. But to get this log n, you really need this thing called AKS sorting networks, which have very, very large constants.
So it's like path ORAM and circuit ORAM still the best practical ORAM.
Yeah. And you can make it, I think you can make an argument for this one, for small enough data. This is squared n log n. But yeah, but not this log n is not anywhere close to practical, but asymptotically it's the most efficient. Great question. Okay. So far, the power of the adversary that you've considered is basically a passive adversary that's just going to answer all these queries honestly, but it's still going to try to do some detective work. It's going to look at these query responses and try to figure out some information about this. But in reality, you can imagine an adversary that does a lot more. So what if you consider an active and malicious adversary that modifies the contents of the server? So basically that the server can be tampered with and this guy can go in and change all the entries. And now all the responses here could be wrong. So immediately it should be quite easy to see that this could break correctness of the ORAM because all these responses here could just, be completely nonsensical. But what's less obvious maybe is that this also breaks obliviousness. And intuitively, the reason this happens is that after a corrupted server response, so after this corrupted server response, the next query could be very leaky. So there's no longer any obliviousness guarantee from this interaction. So this will end up being a big issue. And actually, I'll try to outline a replay attack on an ORAM, like an actual one that's later. So, okay, what are some, looking back at our applications, if a file storage platform like Dropbox and Google Drive tampers, you have no more privacy guarantees. Again, in the secure enclave setting, if someone is able to tamper the untrusted memory, again, you have no more privacy guarantees. So this is a model we should definitely consider. So now let's try to define malicious security. This slide might be a lot, so please ask me questions if anything is not clear.
Is this the first word for malicious security for ORAM?
This is not the first one. Yeah, we'll talk about that in a couple of slides. So you want correctness. So from the user perspective, you get no incorrect response from the ORAM. So you want it to look as if from the user's perspective, you're dealing with an ideal RAM. like an angel that's just going to be an oracle that gives you correct responses. From the server side, the server shouldn't be able to learn anything other than maybe the number of queries. And the only power you want to give the server is the power of aborting. Yeah.
If the server is malicious, then wouldn't we always get the wrong answers? Like how does ORAM play into this?
You want to protect, you want to detect this. Even detecting these wrong answers is not easy.
Okay.
So you're basically either going to force the server to be truthful, or if it's an uncooperative, then so that's why you're going to say it has the power to decide when to abort, because you can always have an uncooperative server. But if it's cooperative, you shouldn't be aborting.
But I'm the one aborting, not ORAM.
So this is like the ideal model. So we're saying that in the ideal world, the server's power is only deciding whether to abort. So that could be because he sends back wrong responses and then you decide to abort. Does that make sense?
Okay.
So this is like the idealized, ideal picture that I'm trying to draw now. But what I'm trying to say is essentially the best thing you can do is determine when to abort. Yeah.
Is it basically saying like every time like the server seems to be wrong things, I can detect it? That
Kind of. It doesn't need to be immediate though. It's a bit weird because what happens is sorry. So okay, I did grayed out. Maybe next slide would have a better picture. So the thing is, you have one query here and a bunch of queries here. So you just have to detect if one of them is wrong. You don't have to detect if every single thing is wrong. That's actually a distinction that'll come in later.
okay.
Yeah. So, okay, so this is the ideal world. Like in the ideal world, we just want it to look like this. But the real world looks like okay. Okay. So in the real world, you have ORAM in the middle. Okay. So first, we can note that because we want the security to be over all the users, you can also think of the user as being malicious, because you're trying to maliciously choose the sequence to fool the ORAM in the middle. And even more, you can even think of the user and server colluding to try to come up with the worst case scenario for the ORAM in the middle. So this is like standard UC type definitions where you're assuming the worst case scenario. So the way we're going to define malicious security is by saying that this environment here that's controlling both the user and the server cannot tell whether it's sandwiching an ORAM or sandwiching an ideal RAM with the simulator. Yeah, this is a lot. Any questions here? So basically this type of like colluding definition is like very typical in UC type definitions. And it's just saying that in the worst case scenario, this could happen. And even then you can't distinguish between the ORAM and the ideal RAM. But of course, you also need like a completeness condition, which says that if the server is honest, then the ORAM doesn't abort. So that, this becomes slightly non-trivial. Okay, any questions? Okay. So going back to ORAM history, let's look at which ones of these are maliciously secure. So Goldreich and Ostrovsky actually agreed that, argue that their constructions can be made maliciously secure with the same overhead. ORAM does a very nice observation that because it's tree based, you can actually put a Merkle tree in like interleave with a Merkle tree with no overhead. But this does assume collision resistant hash functions over not just one-way functions. But Panorama and ORAM are not known to be maliciously secure. And in fact, I'll show some attacks on these later. From the lower bound side of things, we actually don't know if there's any separation. And for all we know, maybe that it's not possible to get a log n ORAM, maybe log squared n is the best. So we can also ask, is there any stronger lower bound for the malicious setting? Because we're asking for a lot more. So that's exactly the problem we consider. So is there a maliciously secure ORAM with O log n overhead? And our answer is yes. Assuming one-way functions, we construct Macorama, which is a maliciously secure ORAM with O log n overhead with O1 private space. Yay, very exciting. So to put it back in this table, Macorama fits here, and now we have log n overhead with malicious security. And as a corollary, we also show that this omega log n lower bound here is tight. Yeah.
I guess I have a question. Don't you get it like in a straightforward way just by composing ORAM and let's say 2-round RAM delegation?
Does that require server-side computation?
Yeah.
Yeah, so ours avoids that.
I don't want to have.
Yeah,
those,
you want to stay in the RAM model. Yeah, but it's actually, I guess that, I don't know about RAM delegation. Okay,
RAM delegation requires the backup.
I see. Okay, yeah. So we are trying to avoid that because the lower bound doesn't apply in that setting either. The lower bound really assumes like a passive storage. So we were trying to get a passive storage of login construction. Okay. So a few comments about our result. So again, our old login overhead is optimal. So essentially we got malicious security on top of the honest but curious ORAM for free. Very exciting. And then our malicious secure ORAM is still in the RAM model. So that means, again, we have no extra work on the server side if it's honest. I mean, adversarial server can do whatever it wants, but an honest server should not have to do any additional work. So it's only going to support read and write queries. So to comment on this one-way function assumption, turns out that for maliciously secure ORAMs, you need one-way functions. This is not true for semi-honest, honest but curious ORAMs necessarily, because if we ignore the data part. So if you assume encryption is a black box that you can just use, you can actually get statistically secure ORAMs. But this is not true in the maliciously secure world. And if you want to distill exactly why we need one-way functions, essentially if you give the client access to a private random oracle, so that means you have like unlimited randomness that only the client can access, but not the adversary, then we can actually get statistical security against unbounded adversaries. Okay, any questions? Okay. Yeah. So let's dive into the construction. This doesn't work. Okay. So as a starting point, we use ORAM, which is construction by Asharov, Komargodski, Lin, Nag, Pasrico, and Shi. This is an curious ORAM in what we call the hierarchical paradigm with optimal O-block overhead. So there's a subset of authors that also showed the worst case O-block was possible. So these 6 authors came out with ORAM, and then there was worst case ORAM. So I'll refer to it as worst case ORAM for the worst case version. Okay, so a little bit of background on hierarchical ORAMs. So the Goldreich and Ostrovsky construction that was long cubed in was what started this line of constructions. So they call it the hierarchical paradigm. So I'm going to describe it on the slide, but I promise there are pictures on the next couple of slides if it's confusing. So basically, you're going to have log n hash tables, which are all so-called oblivious. So that means if you make a lookup, you're not going to leak what you're looking up. And hash table hi has size 2 to the I. So you have a hash table of size 2, 4, 8, 16, so on until size n. So each logical lookup, each logical query that the user sends to the client has a lookup and a rebuild phase. So in the lookup phase, given a query to address, you're going to look for address in each of these hash tables until you finally find it. Once you find it, you're going to keep making dumb lookups to the subsequent tables. And that's essentially to hide exactly which table you found, you address it. And then at the end of the day, after you make all the lookups, you're going to write the updated address back into the smallest hash table. And that'll be pictures of the promise. And then there's a rebuild phase. So intuitively, like if you keep writing back to H1, that's going to overflow. So every 2 to the I queries, you have to rebuild. So you're going to merge the first I hash tables into HI plus 1. So while doing so, you need to remove duplicates, but you can just do that by keeping the version of any address in the lowest layer, smallest layer. Okay, I have pictures now. So now you have these hash tables, and suppose you're trying to look for address. So what are you going to do is on the first hash table, you're going to look for address, you don't find it. Second hash table, you look for address. Okay, yes, you found it. So you're going to keep data 2 locally, but now you can keep going by performing dummy lookups. So you keep going, and then you keep performing dummy lookups. And then at the end of the day, you're going to write address back into H1. Okay, so that's the lookup phase. And this data prime here is going to be equal to data 2 if the query was read, and you're going to update the value if the query was write. And then there's a rebuild phase. So in the rebuild phase, every 2 queries, you're going to merge H1 into H2. Every 4 queries, you're going to merge H1 into H2 and H2 into H3, and so on. So let's try to look at what second thing looks like. So first, you're going to merge H1 and H2. And here, because address was in both layers, we're gonna keep the one in H1 because that's the most recent updated version of of address. And then now you're gonna merge everything into H3. So note that things are shuffling. So by rebuilding, you're also kind of introducing new randomness so that any correlation with previous queries can be hidden. Okay, any questions? This is a very high level idea of what this looks like. Yeah.
I was confused that if you just use a map, it wouldn't work, and you know when each position was last written. So why not just use a map?
Yeah, I'll actually get to that. I'll get to that. That's,
Uh-huh.
yeah, that's the next thing I'm gonna talk about. But there's still some attacks that still work, even if you map things. And also, yeah, okay, I'll get to that. So really quickly about the efficiency of this scheme. So each of these lookups hash tables can be reduced to all one query. And this is very interesting because it's based on Oblivious cuckoo hashing. Cuckoo hashing is just a way to create a hash table with one lookup time. It's really nice. So each of the lookups, each hash table gives you one contribution in runtime. Then suppose the rebuild step happens every 2 to the I steps, and it takes time t of 2 to the I. Then the way you compute the runtime is this is from the lookup phase and this is from the rebuild phase. So every 1 over 2i fraction of the n steps, you're gonna do a t of 2 to the I work. And then if t of 2 to the I equals to O of 2 to the I, so that means the hash table rebuild time is linear, then you can get O log n efficiency. But at this point, I want to really point out that this is very, very difficult to get to. This has a lot of details that I'm really overlooking here. So yeah, ORAM and all these constructions are wonderful. If you want more details, please look at the papers, but that's not the focus of the talk today. Okay, so how can we get malicious security? And as the link suggests, we're going to use Max, and that's why we're going to call it Macorama. So what if we use Max? So what are Max? We just ensure that the server can't forge any new data. So what you're going to do is every ORAM query, you're going to send it over. You're going to add a sigma here. And this sigma is also going to add this address hat in there so that the address hat, you can't move around data. And you read address and so on. And you only accept if the sigma is a valid tag for address computated. So you can just do this. So this forces the server to only send back values that it has already seen. So, but it turns out this is actually insufficient because the server can still do what we call replay attacks. And for example, if the server sends back data old, sigma old, the verification should still pass, right? So this will make the ORAM accept old data, so this is bad. And this turns out to affect both correctness and obliviousness, and I'll show an explicit attack right now. So a replay attack for a hierarchical framework. So the key fact is that you can't make the same lookup twice to a given hash table because you'll end up looking at the same things in that hash table. But if you look at the same address twice in, yeah, that's exactly what I just said. In the honest but curious setting, we kept doing this dummy lookup things and we kept rebuilding the hash tables to ensure this doesn't happen. But if you do replay attack, that's quite devastating. And here's a picture of what, okay. So suppose you're trying to read to address. So you're going to look for address in H1, address in H2, address in H3, and you find it. And then you're going to keep doing dummy lookups. Oops, but that's a typo, that should be dummy. And you write it back to H1. But now suppose you do another read to address. You're going to look it up, look for it in the first hash table. But then, you know, the server's like, what do you mean? You never wrote anything here. And pretends it's not in hash table 1. So it's not found. And you can keep going. And now the thing is, you're going to keep looking for address instead of performing a dummy lookup. So now the access pattern in these 3 layers looks exactly like the previous read. So this is bad because now you leak the fact that we just had a duplicate read. So crucially, you need the fact that the obliviousness of any lookup depends on the correctness of all the previous lookups. This is attack makes sense.
How the server can figure out that in the first layer that figures out.
That what? You can just pretend it was never written to.
Oh.
Yeah.
But I guess for every location you can compute when it was the last time written, so you can find
I
that.
think that's my next slide. Yes. This is true. Yes,
So but you.
but it's not sufficient on its own.
This still doesn't work.
No.
Oh, that's surprising.
Yeah, I agree. That's exactly like in a couple of slides. So, yeah. So as it is, max alone are not sufficient because it can't prevent replay attacks. So it's still maliciously insecure. So it's there are picks. So Goldreich and Ostrovsky in the original paper noticed that you can simply timestamp things to avoid replay attacks. So what's timestamping? You're going to keep track of a local global counter to count the number of queries that you've seen, so you've done so far. So here, very crucially, these are query paths. So this is between the client and the server, you're not trying to timestamp the queries that the user is. So this is a very important distinction here. So for each write, what are you going to do is you're going to include this counter in all the max. And so when you do read, you're going to make sure this counter is correct by using this prep time function. So prep time takes in the current counter and the address that you're reading and computes the last time it was updated. So the theorem that Goldreich and Ostrovsky show is that if the ORAM has a locally low space computable prep time function, you can always verify all of these counters by simply timestamping and this allows you to convert an honest but curious ORAM to a maliciously secure one with the same asymptotic overhead. So pictorially, just to make it more clear, suppose that you have this database and everything's mapped and the current time is counter. You read address 3 and you get back data 3 counter 3 and you just check that prep time of this is correct. So that because counter 3 is correct, it's the last time that this address is written to. So if this check passes, then you know this is the freshest copy. But if you replace it with something older, then counter old has to be smaller than counter 3. So you detect a replay attack and you abort. Okay. But turns out timestamping is not possible for ORAM because of some subroutine. And so as an example, we'll talk about this toy problem marking, but this actually shows up in both Panorama and ORAM. So suppose you have a table and you have to mark positions PI in an online way. So that means you're gonna mark P1, P2, P3, and so on. If you have a prep time function for this, you can recover all of these PIs. Does this make sense? So all of these positions can be recovered, but if you pick the sequence randomly or adversarially, you could have n log n entropy. So even if you have O of n bits of space, you cannot timestamp this, let alone O of log n bits. So there are parts of ORAM that are not deterministic, and you can't timestamp. That's like the high level idea here. Any questions? Okay. So to summarize what we've talked about so far, in hierarchical ORAMs, max alone aren't sufficient because you still have replay attacks, but timestamping can prevent replay attacks. But although the original Goldreich and Ostrovsky construction was timestampable, the new ORAM and Panorama construction are actually not.
I guess I'm a little bit confused. So this marking, is it during the read phase?
So okay, what happens is in the hash table when you make the reads, you have to mark all the visited elements. So they're very adversarially chosen, so you can't timestamp all of those. And if you don't check those when you rebuild, then you could leak duplicate reads.
So you need to mark it.
Yeah, you need to mark it for deduplication. So not you have to remove any red things because you need the residual randomness, right? So you need to remove anything visited so that the remaining things are truly random. Is
it guaranteed that those visited positions will not be read again? And if you mark it as one, it should not be visited again.
Yes, but when you do the rebuild, you need to know what was marked so you can remove them.
Yeah, sure, but I feel like as long as they are not going to be read again, you can, like, you don't have to worry about.
I think in the worst case thing, it actually might matter. I remember I wrote down some attack, but I don't remember what it was right now. Let me try to think. Maybe I'll get back to you on that later. I remember I wrote something down that would be great because of the
to understand, because like intuitively you don't have to read it ever again until
yeah.
until the next time it's being rebuilt.
Mhm.
I feel like we shouldn't have to worry about.
Yeah, I think it's because later when you, oh, I see what you're saying. Yeah, I think I had a hack, I'll tell you about it. Yeah. Okay, so the second technique we're gonna look at is memory checking. So a memory checker is a protocol between a user and a server that's going to verify whether the server is correctly responding to the user's read and write requests. So here's a picture. So the user sends a read and write query. The memory checker has a conversation with the server and sends back a response. So if the server lied, it could either abort or try to come up with a correct response, like try to recover a correct response nevertheless. And for completeness, if the server behaves honestly, then the memory checker doesn't abort. So that means if the server is honest, this is just gonna all pass. So one thing I want to point out here is this is basically the same properties that we needed from a maliciously secure ORAM, except we don't have obliviousness. So a maliciously secure ORAM would imply memory checking, a memory checker. Does it make sense? Okay. Okay. So what's the efficiency of our memory checkers that we know? So just like ORAM, we care about both local space and overhead. And for O1 local space, the best known constructions achieve O log n efficiency. So think of Merkle trees, for example. So if you store the Merkle root locally, that's the O1 local space, then you can just access the path in the binary tree to verify any given read or write response. So the log n comes from the fact that the height of the binary tree is log n. And there's also a lower bound by Bork et al. That says that log n over log n is the best you can do for any memory checker that has a deterministic non-adaptive access pattern. So like Merkle tree, if you know what index you're accessing, the path that you're going to traverse is deterministic and non-adaptive. So for all such memory checkers, log n is essentially somewhat the best thing you can do. So intuitively, memory checkers seem to solve the problem of maliciously secure ORAM, because you can just compose the honest but curious ORAM with the memory checker to get a maliciously secure ORAM. So the high level idea is you can just have a memory checker sandwich in between the ORAM and the server, and then now call the composed thing the maliciously secure ORAM. But the issue with this is that it's not efficient enough, because now you have an overhead of log n from the ORAM and an overhead of log n from the memory checker to get log squared n overhead for your maliciously secure ORAM. So then one thing we can ask is, can you get away with a weaker compiler than a memory checker? So for example, you have some other pi here that isn't a memory checker to compose the ORAM, get a maliciously secure ORAM. What we prove is that any such pi, if it has blow up L, then this better be a memory checker with blow up L. So basically any compiler that looks like this has to be a memory checker. And intuitively, the reason is that you can force a mistake from pi by putting in a very adversarial sequence in ORAM and have the server respond to it maliciously to force a mistake. And the moment you have a mistake, the ORAM can behave arbitrarily. Does that make sense? So the ORAM can just detect the mistake and start saying, okay, I'm not going to be ORAM anymore. And that would still be an honest but curious ORAM, but not a maliciously secure ORAM. Sorry. But yeah, not a maliciously secure ORAM. So essentially, we have to have a memory checker if you want a picture like this. So to summarize what we have so far, we talked about MAX, but MAX don't prevent replay attacks. But we can use timestamping with MAX to prevent replay attacks, but ORAM cannot be timestamped. So we tried to look at memory checking, but we saw that any overhead 1 post compiler would have to imply O1 overhead memory checker, but we don't know how to do that. And the best memory checkers have O log n overhead, so this seems unlikely. So how can we proceed? So we have to essentially handle ORAM in a white box way. We have no other choice. Okay. Yeah, so the question now is, does ORAM need the full power of memory checking? So what if ORAM is okay with some lies from the server? So you use it in the query, ORAM sends query hat. and gets back something, but it looks at it as that, this could be fishy, but I'm okay. I'm just gonna handle it later and I'm gonna proceed. If this query here still doesn't leak anything, given that the previous query was malicious, then we're in good shape. So our idea is to use a weaker but more efficient notion of memory checking to capitalize on this fact. Okay, so this I'm going to introduce offline memory checking. So offline memory checker is basically a memory checker with a slightly weaker correctness condition. So the point is the user is going to send a query. You might get back a wrong response, that's okay. You can send more queries and you keep doing it. And then the user says, I'm done. Tell me whether these responses were correct. And then now the memory checker is going to keep talking to the server to determine whether everything was correct or something went wrong and I'm going to abort. So really think of this as batching a regular memory checker. Does this make sense? So you don't even need to report where the mistake was. You just have to detect that some mistake had happened somewhere. So the main benefit here is that these these constructions with amortized O1 overhead. So this was a result of lump it all and work it all. We take these constructions and we augment it to leave the memory in a so-called verifiable state. So what this means is that after you complete the offline check, this whole memory cannot be tampered with and can be verified with a single query. The main con of offline memory checking is that it's insufficient. So going back to the replay attack that we saw earlier, yeah.
Does this O1 overhead make any assumption about the batch size?
Yes, it needs to be the size. The number of queries has to be at least the number of database entries.
Number of queries.
So like it's O(n) plus the number of queries, where n is
The
the
batch
database.
is very large.
Batch is at least size n.
I
Yeah, size of the database roughly. But it turns out that wherever we use it, that's satisfied.
What were you using? It's not the whole data. Is it like a smaller and?
It's smaller, yeah. So
So
it's like,
using some smaller data.
like each hash table, for example. So recall that we really needed the HI lookup to we needed the HI -1 lookups to be correct to guarantee the obliviousness of the lookup to HI. So an offline check alone would not prevent this. So we need to really combine different types of memory checking here. So when is offline checking safe? So one notion that we define is access deterministic algorithms. So we say that a routine is access deterministic if the list of addresses accessed are completely deterministic and independent of the input in the honest but curious set. That's a lot of work, but basically it's just going to have deterministic access patterns. And this is a stronger notion than just obliviousness, because you could have a randomized access pattern in oblivious office. So for the very special case where the subroutine is access deterministic even against malicious responses, then you can just offline check this. So what do I mean by this? So think of a linear scan. If you're doing a linear scan, you look at the first query, even if you get the wrong answer, you're going to proceed with the linear scan as if it's correct. So you would always do a linear scan no matter what the responses were. So you can just offline check something like that. Sorry. Oops. Another example is like a simple sorting network where you can locally compute all the gates of the network. So all the comparisons you make are determined by the gates. So even if you get a malicious response, you're still locally computing like the comparisons to make. So it doesn't matter if you get a malicious response. So in both of these cases, offline checking is safe because an adversary or server doesn't see any change in access pattern. And you get correctness because the offline check guarantees correctness. Yeah. But turns out if you only have access to deterministic algorithms against the honest but curious setting, offline, it may not in general be offline safe. This is very subtle and it's somehow implementation dependent. So, but nevertheless, we show that if a subroutine is access deterministic, even in just the honest but curious setting, you can always make it maliciously secure with the same asymptotic overhead. One interesting interpretation of this is that every access deterministic algorithm has the prep time function as we define in the timestamping portion. But it makes no assumption about this prep time function being low space computable. So it could be have a very difficult to compute prep time function, but you know that one exists and a deterministic one exists. So this is the idea that we capitalize on.
I guess I'm not following you. So why is it not offline based and completely deterministic?
Okay, yeah, actually, you know what? I had a bonus slide. Let me just get to that then. I had a bonus slide. Okay. But I'm gonna make this go away. So consider the following implementation of an AKS sort. So first, you're gonna compute the bipartite expander. So the list of edges in this bipartite expander. So the AKS sort depends on the bipartite expander, and you make comparisons according to that. Then you iterate over the edge set E of the graph and make comparisons according to this edge set. But if you like replace any of this E edges with something that contains sensitive secret data, your access pattern is going to leak that secret data. But if you instead did the same thing, but you locally computed this bipartite expander, then you wouldn't have this problem. Does that make sense?
Yeah, maybe I'm missing something. But
Yeah.
I guess like,
The point is you can if you compute the access pattern like this, you compute the expander on the sky. Now the server can tamper with it. But the server can also inject secret information in it, and your access pattern is going to now leak the secret information.
I thought you said the access pattern is deterministic, that depends on the context.
But only in the honest but curious setting.
Oh, I see. So
Yeah.
That's the difference.
Yeah, that's the difference. So somehow this is implementation dependent. Because you can implement this in a secure way by locally computing the bipartite expander, for example. So we wanted a implementation independent theorem. That
So
didn't,
you are saying by, I guess like the only possible example is by making malicious attacks, like it's kind of internally inconsistent, because if it's internally consistent there, you can always recover an input consistent with it.
sorry, can you say that again?
Is it because like by making malicious attacks, I can give you data that's internally inconsistent?
Yes, exactly. Yeah. So you could have, even if the Mac attack would not solve this, because you can imagine maybe the same space was used to store some sensitive data before. So you can still do a replay attack to put it back in the previous state, to put very sensitive information in place of the bipartite expander. So the point is like the implementation of the algorithm seems to be very important in this transformation.
Yeah, so I mean, I don't understand this concrete view of the AKS network, but I guess my understanding is that it's like if the data I get is correct, you are seeing some algorithm's behavior will change when the data is correct. It's not guaranteed how it's only guaranteed how it will behave.
In the honest, when
When
it's
you are
correct.
being consistent.
Yes, exactly. Yeah. I'm going to go back to the previous slide. Let me move this. Okay, so the high level idea is that you can use offline checking to pre-process the prep time data structure for this algorithm. So you can run it on some dummy input to compute this prep time data structure. And by offline checking, you can guarantee that this is correct. And then now you can proceed with the time stamping type method to timestamp the algorithm using the Goldreich and Ostrovsky idea. Does this high level picture make sense? So because offline checking is linear time, computing this data structure is linear time and efficient. So you can view this as a strengthening of the Goldreich and Ostrovsky theorem. So unconditionally, no matter what the prep time function is, we can always have this make this transformation. Okay. Any questions?
Yes, I guess this is just saying I'm just going to, like, if the algorithm has this weird behavior, I'm going to remove this weird behavior and have it always act as deterministic.
Yeah.
Deterministic set of those.
Yes.
Thank you.
Yeah, that's the idea. Okay, so in an ideal world, you timestamp whenever you can, and hope that everything else is acts as deterministic or offline safe. Unfortunately, this isn't true, and there are parts of the algorithm that are not timestampable or acts as deterministic or offline safe. And how do we get around this? So there are parts where we have to combine timestamping and offline checking within the algorithms. So I'll give a baby example here. So consider this toy problem of hashing balls into bins. So this actually comes up in Optorama. So you have a bunch of BI values. So the values BI are going to be hashed into bin BI. So suppose for now the BI is safe to leak. So for example, they were like completely uniformly random. Then the only thing leaked, so the way you're going to do the hashing is you're going to look at this B1 and you're going to hash it. Look at this B2 and you're going to hash it, and so on. But if you tamper with this BI to include some private XI, the access pattern will leak the value of XI. So this is very similar to the bipartite expander I just mentioned. So if you tamper with the values here, the access pattern is going to leak X1. So not good. Oh, sorry. But it is offline safe if you can ensure that the BI array is not tampered with. So what you can do is you can timestamp this array. And then you can offline check the remaining hashing. So every time you make a query here, you're going to verify the timestamp. So you're conducting an offline check over this guy. So based somehow you're like combining offline check with timestamping to get security. So in summary, there are many routines which are what we call conditionally offline safe. So if you just timestamp whatever part that needs to be tamper-proof and conditioned on that, everything is offline safe. So this is the high level picture of what's going on. Okay. So this helps to convert from honest but curious to malicious security with O1 overhead. Or O1 blow up. Okay. So that brings us to the end of the talk. To summarize, so we construct Macrorama, which is a maliciously secure ORAM with optimal O of login overhead and O1 local space. So another interesting interpretation of this is that we actually constructed an oblivious memory checker, because memory checker was a weaker primitive than a maliciously secure ORAM. And it achieves an O of login overhead, which matches all existing memory checkers. So somehow we get obliviousness for free. Our assumptions that prove really minimal because one-way functions were necessary. And we also showed that an overhead preserving compiler that's black box has a barrier. So instead we develop a bunch of memory checking techniques that we can use. And we believe that this can be generalized in future ORAM constructions or maybe even data structure construction. So to leave you with the open question, so is there any maliciously secure ORAM with a small constant factor? So as I mentioned before, Optorama inherently has a very large constant factor. So, and I think our transformation on top of that maybe as like a 10, like constant of 10. So there's an open question even in the underlying like ORAM literature of constructing O of login overhead, small constant construction for all word sizes. Another question is there any memory checker or black box compiler that has O of 1 overhead, or can you show unconditional lower bound against such a thing? Thank you. Question?
Could you go back to the last one? No. Yeah. So talk about the constant factors being large. So is that is the constant factors for access or query numbers, like the compiling overhead? So you're compiling physical access to the access between the ORAM client and the server.
Actually, no, logical access. Yeah.
Oh, okay.
Yeah. And that has a very large constant factor because the rebuild phase uses a lot of bipartite expander type magic, which has a very large constant factor.
So for example, originally you compile one access to, for example, 10 accesses to the server, and now you have like 100 accesses to the server.
Yeah.
I see.
Yeah. Oh, yeah, our overhead is like, yes.
Okay.
Yeah, okay. 10 is a loose bound, but you should at most 10, I think.
So for the second question here, if I'm able to design a memory checker with O of 1 overhead, that guarantees that I can just compile Optorama to a maliciously secure one.
Yeah,
for free,
and
right?
I'm out of this, but yeah. Yes.
But isn't that impossible?
No, because it's just that there's no existing O of 1, right? There's no
Yeah.
lower bound.
Yeah,
Only
there's no
the
lower bound unconditionally, but like
Mhm.
there is a lower bound for some types of memory checkers, but not an unconditional lower bound.
so it needs to be a like a full memory checker, right? Not like this average. For your
yes,
like, for the
yes.
overhead.
Amortized O1 would be interesting.
What do you mean by computational? I don't want any computational.
No, sorry, I meant, no, I meant no lower, restrictions on the type of memory checker, because before we had a lower bound for non-adaptive deterministic, sorry, that's poor wording. So there's a lower bound for non-adaptive deterministic, memory checkers, but not like any arbitrary memory checker. So you could have like a randomized the memory checker with randomized access patterns that has O1.
What's the low bound for not adaptive?
Log n over log n. It's by Dwork, Nauer, Vinod, and Rosenthal.
Not adaptive and.
And yeah, non-adaptive in the sense of the access pattern. So if I give you the query, the addresses you're going to access are all like determined by just the name of the query. So like a Merkle tree would fall into that category because you know the path that you're going to access given the query. But if you could have like a randomized adaptive thing, that so even if it could be deterministic and adaptive, so you can make a query and then based on the response you make a deterministic query, but even that might be okay.
I see, so for adaptive, it's not known that, and it's
Yeah.
no lower bound.
No lower bound. Yeah, so that was poor wording, sorry about that.
Have there been words on two server models, like let's say I have two servers for storing the data?
Two server there are, but I think all like two server ORAM, right?
Yeah,
I think there are, but I think the malicious security constructions assume server side computation. Yeah, from what I've seen so far. So there are a bunch of constructions actually achieving O1 overhead in the multi-server setting if they can do server side computation.
and how much is that computation? Is that a lot?
I think it's polylog. I don't remember off the top of my head. So there's like one onion ORAM, there's one.
So what's the two server?
In the, yeah.
Oh, two server. I mean, there's one server with server side computation that.
I don't even know what's the best you could do in two server model. Is it still login?
I'm actually not sure.
I mean, there's a log and lower bound at least on the number of locations the servers have to access.
Regardless of number of.
Yeah, the number of servers.
Right,
I see.
because that's just the standard ORAM lower bound. Right.
But maybe you could get a better constant with your,
Well, it's two servers and is it still? I remember it was, yeah,
I think it's yes,
no.
but I am not entirely sure.
How many subroutines is the ORAM needs to do you need to open up the boxes and then to.
So most of it happens in the Oblivious hash table build phase, but then that also uses a bunch of algorithms. So like that, but that's where most of the work happens. Yeah. For most of it, we can apply this access deterministic theorem.
I see.
The more randomized ones we have to open up.
Going back to the hashing, right? So you said something about you have to offline check the previous hash before you can continue, right? Going back, like,
This part
yeah, so here when you do the hashing, right, you're saying you have to offline check.
online, the timestamp.
Oh, yeah, sorry, but then if I'm malicious and I choose incorrect value for like B1, let's say, and then I hash it, isn't that fine to not check until the end because I already know what that value is, or no? Like why do I have to do the time checking?
Timestamp.
The
So
time
to make sure
checking.
that none of this is tampered with. Because if you can replace any of these, then you can end up leaking private data. Maybe I'm not understanding them.
But the private data is something that I chose, right? So it's like, what do you mean by
Okay,
which?
So here, the point is that if you replace one of these BIs with some X1,
Okay.
then you would hash according to X1 and you will leak the
Oh, okay.
value of X1. So you have to make sure that nothing here is messed with.
sorry, again, back to two server setting.
Yeah.
The reason I asked you is that like assume there are two servers and they have like process data.
Mhm.
Now, what I could simply do is just ask them the same questions, and if they respond same, then, and I assume one of them is acting honestly, I still have some sense of guarantee that this, like, the,
I think, if you use, okay, there's a few things. Are you gonna use the same key with both of them?
yeah, I mean, if they
If
come
you use the
together,
same
then
key, they can like,
I'm willing to assume that they don't cooperate with each other, like they're.
they do not cooperate at all.
Yeah,
Then maybe this could work. Maybe it could work. But they could like agree previously on a strategy, for example.
that they could do.
That then it wouldn't work, right? If you use the same key. So you would have to use a different key, but if you use a different key, how do you verify against each other?
Yeah. But maybe there's some algebraic approach to.
I see, yeah. You're trying to stay in the vaults and bins model. Yeah, we tried to stay in the vaults and bins model for this construction and the RAM setting. I think there are constructions of function secret sharing across multiple servers.
Yeah, that's PIR. right?
Yeah, that's the PR.
There's also PIR based ORAM schemes that do this.
Can you also explain the difference between PIR and ORAM and where
Yes.
one?
Great question. So the main difference is that PIR is a public database that many clients are trying to access. So that you're not trying to keep the database private, and it's not going to be stateful. I know that the DPIR construction is actually updatable, but but in the classical setting, you don't assume it's updatable. You assume it's a static database. Here, you have a single client that can be stateful, and it's updating the database. So you're only catering to one person, and the database is dynamic.
And also the database starts like with all zeros. So I think that.
You could also set up the database, actually. You could have it
I mean,
set
the
up.
database
phase-
is public. right? So
Oh, you're
Yeah,
like-
and PIR, the database is completely public.
Oh, so you're saying that we can start from a public
Yeah.
database and then update it?
Yes,
Mm.
yes, that could be fine. You can define a setup algorithm that just,
Yeah.
like writes sequentially. So that's a subtle difference.
But the PIR approaches, you cannot get the logman overhead, right? Because you like.
On,
They're from the Boston bits model because.
Yeah, okay,
Yeah.
Oh,
because you
so
like
that-
Vinci and whatnot.
Yeah.
So that's not.
Yeah.
Yeah, you also need server side computation.
Wait, I'm
So
still confused. If you start with a public database, then if I just do one access, just do one read,
okay.
why isn't that
The setup.
better than?
Setup itself.
They have a preprocessing that encodes the data
Yeah.
on the server.
Yeah,
Oh, I see.
Yeah.
So it makes it be linear in the tree process.
Yeah.
So now the PIR more than twice.